Let's talk about racing cars. Over the next 40 minutes or so, I'll talk to you a little bit about the science of vehicle dynamics, particularly how it relates to Formula Student, or at least that's the aim. It's going to be a bit of a whistle-stop tour through some vehicle dynamics concepts, and there's far more in this subject that I'm going to have time to present over the next 40 minutes. But at the end, happy to answer any questions, recommend some good books, something like that. A little bit about my background. I attended Loughborough University studying automotive engineering, and I was head of design for the LU Motorsport FSAE team. I did my final year dissertation on modelling of Formula One dampers, and since then I've spent 13 years working in Formula One vehicle dynamics at two different teams, specialising in performance development using vehicle simulation. So, let's make sure you're still all awake. What we're going to do is we're going to go through the 5 items that are going to dictate the finishing position, the overall performance, let's say, of your car in the Formula Student competition. So I'm going to flash up some images. They're going to represent one of each of the things, and it'll be up to you to kind of call them out as you see them. So here's number 1. This is a Caterham This is a Caterham Superlight that goes around the Top Gear test track quicker than a Bugatti Veyron with 1,000 horsepower. What are we getting at?
Yeah, power to weight ratio.
Ah, well, let's just call it weight to start with. This next image, our friend Valtteri struggling a little bit on a damp track. We could call it traction. Traction good. Tyres, grip. Next one. What does this guy understand?
Power.
Absolutely. Here's a chaparral from the 60s. Aerodynamics. And finally, absolutely right. There's a hidden 6th one, which we'll call reliability. The old adage, to finish first you must finish. But everything we talk about today isn't as important as these 5 aspects. These are your primary objectives for making the fastest racing car that you can. Everything we talk about today is more an opportunity for failure than it is for success. But equally, if you can master all the lessons that we're going to talk about over the next few minutes, then you might be able to, sneak ahead of 1 or 2 of your competition who are sort of equally well placed in these 5 attributes. So the science of vehicle dynamics really starts with tyre behaviour. So tyres generate force by slipping relative to the road surface. So this comes in 2 forms really. Lateral slip, so the tyre slipping laterally across the road produces a lateral force. Longitudinal slip, that is the wheel rotating at a different speed to the ground that passes underneath it. That's going to generate a longitudinal force. And a lot of the time we're going to have some combination of the 2 of these going on at any one time. Particularly in racing cars, you spend a lot of time in combined braking and cornering, combined traction and cornering. And the relationship between the slip that we put in and the force that we get out of the tyre looks a little bit like this. It's pretty common to both lateral and longitudinal slip, but this one is for lateral slip. You start with this initial region of linearity, so adding a unit of slip adds a fixed proportion of force, and that carries on up until a point where this is starting to roll off, and you'll eventually reach a peak that is the maximum grip of your tyre. Excuse me. And if you add slip beyond that, you actually start losing force rather than gaining it. The other important thing to know about tyres is that they're sensitive to vertical load as well. So the grip that you get is a function of how much load you've got on the tyre pressing down. This is why cars have downforce. The important lesson though is that the friction coefficient of your tyre in terms of its maximum grip actually reduces slightly as you add vertical load. So you still gain grip when you add vertical load, but at an ever decreasing rate. And once we've appreciated some of these things, we can build them up into a simple model of the car. So some of you may have come across this. This is known as the bicycle model of vehicle dynamics. In that it acts like it only has two tyres on each axle. There's no lateral weight transfer across the car when you're going through cornering. Not because this acts like a real bicycle. Real bicycles are much more difficult to model. This is just a car with two tyres. And this teaches us a couple of things. First of all, that the sum of the forces from each axle combine to give a total lateral force that acts on the car that you're going to use to do some cornering, but also you've generated a moment about the C of G that comes as a function of the force on each tyre and the distance of each tyre from the CG. A very important case is what we call yaw moment balance. This is where the yaw moments from the front and rear axle cancel each other out at the C of G. This leads to steady state cornering, or it's the case that you get in a straight head condition as well. It's a particular case. You've got no yaw acceleration on the car, so the car is in a steady state going through a constant radius corner. So how are we going to reach this state of yaw moment balance? We're going to start off from the straight ahead position. We're going to add some steer to the front axle. This creates a slip angle on the front axle, and in turn you start to get some lateral force generated at the front. This lateral force creates a yaw moment about the C of G, and you're going to start accelerating in yaw. As you accelerate in yaw and you gain velocity, you start to add slip angle on the rear axle, and when you do this, the lateral force on the rear axle starts to increase, and it starts to balance out the yaw moment generated by the front axle that gave us our initial yaw acceleration. And what we'll find is after a couple of oscillations, you'll settle into your steady state corner. The amount of steer that you need to achieve corners of a different radius leads us to a concept known as the understeer gradient of the car. So what we've got is the expression up here. The terms in this expression are effectively the weight distribution. A and B are the distances of the front and rear axle from your C of G, and your tyre cornering stiffness distribution. So we talked earlier on about the cornering stiffness of the tyre, how that relates, or how the front axle relates to the rear axle is what we call the tyre cornering stiffness distribution. What this expression tells us is that with a forwards weight distribution or an increased rear axle cornering stiffness, we're going to end up with more understeer, relatively speaking. And by understeer, it's quite a specific definition. Understeer means we need to add steer as we increase speed to stay on the same cornering trajectory. By contrast, with a rearwards weight distribution or an increased front axle cornering stiffness, this is tending to oversteer. And again, by oversteer we mean as we increase speed around a certain radius corner, we're going to have to reduce our steer angle. And this is what this last one is. And this is what's represented in this plot here. A bit of a note on stability. So cars with a very negative understeer gradient, you can find yourself limited by stability far earlier than you find yourself limited by the peak grip of the tyre. What we're looking at here is as you added some yaw moment on the front axle and the car begins to rotate in yaw, you come up against a gradient. So that is the yaw moment that you get as you add sort of yaw on the car, or I won't go into in any more detail than that. But what we want to avoid is a situation where, as we add yaw angle to the car body, we get positive feedback, which is giving a moment that adds yaw to adds more yaw to the car. This is how you go and find yourself in a spin. So again, typically this happens when the rear axle has very low rear cornering stiffness, and that can happen when you're approaching the limit of grip. So obviously that your gradient as you approach the peak grip of the tyre is starting to reduce. And this can, in theory, this can lead to a car that spins in a straight line if you've got this wrong. Practically, maybe that doesn't happen, but in an ideal sense, that's certainly the case. So again, what we need here to avoid this is a strong rear axle with high rear cornering stiffness. Move the weight distribution forwards. This will improve our cornering stability and stop the driver having to make tiny corrections every time they go into a particular corner. That's just going to slow them down. Unfortunately, this is about as far as our bicycle model can take us. We're going to have to go and get our two wheels back. Because longitudinal forces also contribute to the car handling. So, am I right in thinking we've not got anyone in here who's driven the car? Is that right? Has anyone driven the car?
No, not yet.
Not yet. No problem. That means I can say this unopposed. You'll probably find that your Formula Student car has got quite a lot of understeer, and that it's front limited a lot of the time. And when you think about it, that's a bit of a surprise, because you know it's rear wheel drive, pretty short wheelbase, rearwards weight distribution in a lot of cases, because all your heavy stuff is over the rear axle. You know, it's not something that comes too intuitively, and it's sometimes a bit of a surprise when people are driving. So the reason for this comes from the longitudinal forces that are generated by the tyres as you're cornering, particularly in very low speed. So what you can see here is, as you're going around a corner, you can draw the instantaneous centre, which is the point in space that your car is turning around. In a very low speed corner, this instantaneous turn centre is very close to your rear axle. When this is the case, the tyre that's furthest from your instantaneous centre is your front outside tyre here. And this has got, in a low speed corner, it's got quite a lot of steer on it, which adds quite a big scrubbing component, quite a big rearward lateral force as you're going around the corner. And what this is doing is it's adding a big understeer moment into your car in this part of the corner. Incidentally, as you increase speed, this instantaneous centre moves relatively forward compared to the rear axle of the car. This off-tracking goes away. There's a lot of situations where cars have a lot of low-speed understeer, high-speed oversteer. The other aspect we need to include is the differential, because this is a pretty key device that you can use to tune the handling of your car. We can consider two extreme states with the differential. We can talk about a free differential and a lock differential. When the car is running with free differential and it's got the driver's got put some throttle in, you're going to have equal torques on each of the rear tyres. When we lock the diff, the constraint becomes equal speeds, and when that happens, because you're cornering and you've got weight transfer onto the outside tyre, this tyre is generating a lot more longitudinal force. You actually generate a slightly oversteer moment on corner exits. So again here, locked on exits, destabilising, a bit of an oversteer moment, but by being locked on exit you also prevent inside wheel spin. And inside wheel spin is definitely a much worse condition, because all the power that you've got from the engine, where the driver's pressing on the throttle, is going to spinning that wheel rather than driving the car forwards. So a locked diff in this state isn't such a bad place to be. When the diff is locked on entry, this has a stabilising effect on the car. You've got an understeer moment in this condition. You also prevent rear inside tyre locking, which is definitely a situation you don't want to be in as well. A lot of the teams you compete against might use spool drives rather than a differential. So this is just connecting both axles against each other with a rigid link rather than having any differential in between. This isn't the worst idea, but it does add a bit of understeer moment when you're cornering, because there's a difference between your inside and outside wheel speed that you get because each tyre is at a different distance from the instantaneous turn centre. So again, a bit more understeer when you've probably already got a reasonable amount of understeer that comes from the off-tracking that we talked about earlier. So now I'll talk a little bit about how we can start to modify some of the aspects of balance on the car. You know, you're going to have to drive and set up the car you've got in front of you, but there's plenty of things that you should be able to do to maximise the potential, even if the initial handling maybe isn't as you'd ideally want. So we've already talked a little bit about weight distribution and tyre cornering stiffness. I've got a bit of a case study for that. We'll touch on the idea of mechanical balance and also aero balance. So, this is a bit of an inflammatory statement. When we talk about weight distribution, BMW in a lot of their advertising likes to talk about how their cars have got perfect 50-50 weight distribution. And anybody who's understood the understeer gradient equation that we brought up earlier knows that this is no barrier to being away from 50-50 is no barrier to a good handling car. And this is something Porsche understands very well. So on the 911 you've got a lot of weight over the rear axle, but because you've also got freedom over the tyres that you put on your car, you can use this to counteract this effect to a certain degree. And an interesting little trick that you can use to work out a car's weight distribution is to have a look at the relative tyre widths on the front and rear axle. So tyre cornering stiffness scales roughly linearly with tyre width. So given the tyres on the rear axle are much wider than on the front axle, you can be pretty confident that the tyre cornering stiffness balance is very real. Sometimes you see Porsche sports car tyres stacked up next to each other, and you can get two front tyres into the width of a rear tyre. And that's a pretty good sign that you're running at about 65% of your weight on the rear axle. Next to aero mechanical balance. So starting off with a bit of a discussion of mechanical balance, there's a bit of jargon in here. A lot of teams might call this lateral load transfer distribution. What it is it's the ratio of weight transfer on the front axle relative to the rear axle. If you're transferring all of your weight transfer on the front, you've got a forwards mechanical balance. If you're doing most things on the rear, you've got a rearwards mechanical balance. You can tune this by tuning the spring stiffnesses on your car. Stiff corner springs or a stiff front corner springs, stiff front anti-roll bar moves your mechanical balance forwards because as the car rolls, more of the load is taken by that axle, and vice versa on the rear axle. Suspension geometry is also a factor. I'll come on to why a bit later on. Mechanical balance tends to be most powerful in the low speed, Relative to aero balance, mechanical balance is working best when the grip on each axle is a big function of the total vertical load on the axle, let's say. Forwards mechanical balance promotes understeer because, as we looked at earlier, the tyre vertical load sensitivity starts to roll off on higher vertical loads, which means the more weight you transfer on a given axle, the less total grip you can expect that axle to have. Rearwards balance, more oversteer. The other thing you need to bear in mind is that the total weight transfer is pretty much completely fixed. You can't do anything about how much weight you're transferring unless you widen your track and lower your CG, but you can choose how it gets distributed front to rear. But another point that you'll notice with a lot of cars is you can only transfer the weight that's on that axle. So if you've got a very rearwards weight distribution and you want to have a very forwards mechanical balance, what you'll find is that you end up lifting inside front tyres because there just isn't the weight on that axle to transfer in order to give you the handling characteristic that you want. And here, this car is a good example of that. This might be one that has found they've got a lot of understeer, so they've done a good step of mechanical balance rearwards. All they've done is lifted the inside rear tyre, and any subsequent weight transfer has to happen on the front axle. So it's not something that you can just keep hammering forever. Aero balance is slightly simpler. You can tune it, adding wings, adjusting flap angles, switching components on the car. Again, most powerful in high speed. Aerodynamic forces increase with the square of speed. The biggest impact that they have is at the high speeds. Forwards aero balance or forward centre of pressure adds grip to the front axle, gives you more oversteer. Rearwards aero balance, more grip on the rear axle, more understeer. The good thing about aerodynamics is there's probably not, as far as we're concerned, not really a limit to how much you can add in terms of like there is on weight transfer and maximum forwards and rearwards load transfer distribution. As long as you can keep fitting bigger wings, cranking in more flap, then you'll add grip to that axle and maybe you'll go faster. So what I thought I'd do is just talk through the different corner phases that your driver's likely to encounter during the event and what's likely to be limiting them at each phase in the corner, and therefore what they can do about it. So what we'll normally find is that there'll be a particular corner phase that's limiting to the driver, and we'll try and divert all our efforts to improving that in the hope that by curing that issue we unlock performance potential throughout the rest of the corner. So we'll start with straight line braking. Next phase, corner entry, just as you start to turn the wheel. Then we've got our sort of steady state mid-corner skid pad type condition, corner exit, and finally straight line traction, which is pretty much your acceleration test as well. And again, there's something that's limiting performance through each of these phases. Our job is to find out what that is and propose fixes that unlock the potential. So, straight line braking. Both axles here are producing longitudinal force exclusively. The weight transfer is all to the front axle. What are we likely to be limited by? We could be limited by the front axle locking first. When we press hard on the brake pedal, front axle locks. That's going to prevent us from going any quicker or slow down any quicker. Equally, if our brake bias is more rearwards, when we put our foot on the brake pedal, we can lock the rear axle. This is definitely worse than the first option, because when we lock the rear axle, the rear tyre cornering stiffness goes to 0. We end up with that unstable case where a car can spin in a straight line. The other thing we might be limited by is literally how hard the driver can press the pedal. In Formula Student, this will prevent you from competing. It might be that you can't press the pedal hard enough in order to lock the wheels. You need a stronger leg in order to go any quicker. Next phase of the corner entry. This is where the driver starts to add some steer while still on the brakes. Or a good driver will anyway. Here you've got load transfer to the front outside tyre. This tyre becomes extremely strong and has a lot of grip. A lot of the time we could live with a lot less grip on here because all it's doing is adding instability. Here we could be limited by a few different things. So first of all, we could have some front inside tyre locking. If we've got a forwards brake bias and say maybe quite far forwards mechanical balance, then we could find ourselves locking that tyre quite early in the phase. And we don't want to end up with square tyres, so that's going to limit how quickly we can decelerate and the sort of maximum acceleration we can have at this phase. The other thing we could be limited by is rear stability. Again, as the rear tyres get close to locking, with all this forward weight transfer, we could find that the car feels unstable. Drivers making lots of little corrections in order to keep the car pointing straight ahead. And finally, rear inside tyre locking. This is pretty simple. There's not enough diff locking if you're in this condition. Shouldn't really be having to worry about inside rear locking in this case. Then we get to a point in the corner where the driver's off throttle and off brakes. And this is our sort of steady state, yaw moment balance case that we talked about earlier. Here all the weight transfer is to the outside tyres on the car. And for a car that's balanced on entry, we're usually going to find that we've got a lot more understeer in this condition than we had on entry, because all of the weight transfer is undone. Now back to the axles being balanced in similar to the sort of straight ahead condition. This is in effect undoing the extra front grip that you had on corner entry because of that weight transfer. Also, we talked a little bit about off tracking. This is going to contribute to the understeer we get at this phase in the corner. And just a note at the end, so maybe you could consider a more rearwards lateral balance for the skid pad test than you use in the other elements of the competition. Because you're in the skid pad, you don't have that weight transfer onto the front axle in corner entry. You should be able to tolerate a bit more rearwards mechanical balance, just in order to get that rotation in the car and prevent the sort of turning on understeer. Corner exits. This is where the driver is going to start to go on throttle as the corner opens out. The weight transfer is to this rear outside tyre. Again, overwhelmingly likely that we're going to be limited by the rear axle in this case in a rear-wheel drive car, because however much grip you can get on the front axle, enough throttle is going to spin the rear axle. The other thing we might have is some rear inside tyre spinning, as if we haven't got enough diff locking, again, all the power is going to go to that spinning outside rear tyre rather than accelerating the car. That's a position we definitely want to avoid. Finally, straight line traction and acceleration. Excuse me. So here the driver is completely unwound the steering and is moving towards getting to full throttle. In this case, the load transfer is to the rear axle. And again, we're going to be limited by the grip of the tyres on the rear axle and by our total power. Well, by the time we get to full throttle, There's nothing we can do to go quicker with grip. It's all about engine power at that point. What's interesting here in this case with rear-wheel drive cars is actually, because the front axle isn't doing anything at all, what you want is all the weight on your rear axle. So if you could have a very high C of G for the acceleration test only, provided you don't get to a point where the car is wheeling down the straight, that's going to put you in a position where you've got most grip on your rear axle. Similarly, you could move your weight distribution further inwards. So, it is possible that we might be able to address some of these limitations through manipulation of the suspension kinematics. By kinematics, we mean how the wheel changes its position and orientation as it goes through its bump travel. But again, this isn't one of our big 5 things that we've got at the start of our presentation. This isn't going to help much, but sometimes every little helps, and it's good to put ourselves in the best condition that we can. To start with, we can talk a little bit about roll centres. So the roll centre height is quite a key parameter that vehicle dynamicists might look at to decide how the car is going to behave in handling. To construct this is pretty straightforward. What you do is you extend the planes of the wishbones into a point where they meet, and these are the instantaneous centres of the suspension rather than off cornering. We can then draw some lines between these suspension instantaneous centres and the contact patches. And what we end up with here is the virtual swing arms. And this virtual swing arm is, if you reduce the whole suspension system into a single link, this is what it would be. The roll centre height, the geometric roll centre height, I should say, is the intersection of these two virtual swing arms. So what the roll centre does is it defines the ratio of load transfer that you get through the springs and through the wishbones. So a high roll centre, roll centre at the CG height means that all weight transfer goes through the wishbones as opposed to the springs. This is kind of good and bad. On the one hand, you get lower roll angles for the same roll stiffness on that axle because the springs aren't taking up the kind of the roll moment in the car. It's all done by the wishbones and they're very stiff. But we'll also we'll also completely remove our ability to shift the mechanical balance or the lateral load transfer distribution up and down the car, because now none of the roll moment is being taken in the internals in the springs. So that's not a position that any car really runs. You'll also increase the rate of load transfer by passing the load through the wishbones rather than through the springs, because you no longer have to wait for the car to settle into the corner, the body to roll onto the springs in order to achieve that weight transfer. So strictly speaking, you probably lose a little bit of grip by raising the roll centre, because in that sort of transient turn-in phase, the weight transfer is now happening much more quickly. And the final thing we get is some jacking on that axle with a high roll centre. So here we can break out our analogy of a pair of scissors. The reason the jacking force originates is because with weight transfer, you've got more lateral force coming from your outside tyre than you have on your inside tyre. And when you do that with a pair of scissors, the arms close together, this joint in the middle moves vertically upwards. Jacking forces can be particularly positive, can be particularly negative, or maybe even slightly positive. So it's largely sort of application specific, which direction you want to push some of these things in. similar to roll centres, but in the longitudinal sense, we have what we'll call the suspension antes. This is what the antes are doing is they're jacking the body as a result of longitudinal forces on the tyres and therefore longitudinal acceleration, rather than lateral forces and lateral acceleration that we were looking at with roll centres. The construction is pretty similar. Again, you take the planes of the wishbones, but this time in the longitudinal plane. You create an instantaneous centre. Again, you connect your contact patch to that instantaneous centre to create the virtual swing arm. But now, rather than finding the intersection between that and another virtual swing arm, you relate it relative to the CG height. So what we've got here is a virtual swing arm sort of plane that intersects perfectly with the CG. And this is a situation we call 100% anti-dive. And what this means is that all of the longitudinal force at the tyre contact patch is going to be transferred through the wishbones rather than through the springs. So you won't get that dive onto the springs that you would have with lower levels of anti-dive, for example. You'll probably find that the front of the front axle still looks like it's diving, because the springs aren't the only compliant element in the suspension. You've got some internal some external compliances, but also a key contribution is the tyre as well. So you're going to need a lot more than 100% anti-dive to completely prevent any dip under braking. On the rear axle, we can talk about anti-rise and anti-squat. So anti-rise is taking more load through the wishbones on the rear axle in braking to get less rise on the rear axle. Anti-squat is preventing squatting of the rear axle by taking more of the traction force through the wishbones rather than the springs. So the final point here is the point that you connect the virtual swing arm to on the wheel depends on the origin of the torque you're passing through. This isn't something that's perfectly well explained in a lot of vehicle dynamics textbooks, but it's actually quite simple to understand. If your torques are originating from the inboard, so say you've got inboard brakes, or you have or the torque is coming through your drive shafts, because there's a wheel bearing on each of your uprights, you can't transfer any torques from your inboard systems to the upright. So the longitudinal force acts as though it's coming from the wheel centre. On the outboard case, so say you have outboard brakes or hub motors, because the torques you're producing there react straight onto the upright. The upright does take some torque. The longitudinal forces act as if they're coming from the tyre contact patch. So, depending on where your torques originate, your calculation of anti-squat and anti-rise differs slightly. And then the final thing I just wanted to touch on quickly was the idea of steering kinematics. So whilst on the rear axle you probably only have 1 degree of freedom, on the front axle you have steer as well as bump. And by steering kinematics we mean how the position and orientation of the wheel changes as we add and take away steer. Two important parameters you're going to come up against when making this decision are caster and trail. Caster is really good because caster adds favourable camber to both tyres with steer. And if you're steering a long way, it's probably because you've got lots of understeer, and being able to add lots of favourable camber to the tyres in that condition is probably going to help you get round the corner. To work out what the caster angle is, we connect the upper and lower ball joints on the upright to create this kingpin axis, and we extend that, we take that kinematics axis in the longitudinal plane, measure it relative to the vertical, and that gives you your caster angle. And what we end up here is typically an offset between the intersection of the kingpin axis and the ground plane and the point directly below the wheel centre. And that's what we call our mechanical trail. If we add too much caster, if we get greedy and want to add more and more favourable camber with steer, this trail is probably going to get very big. And that's important because this distance largely dictates the steering torque your driver is going to perceive in the steering wheel. So lots and lots of trail means the steering is going to be too heavy. You're not going to be able to go around the corner without massive power assistance. Similarly, if we go in the opposite direction, too little trail means that the self-aligning torque from the tyres is going to completely wash out the effect of the lateral force the driver really cares about when they're trying to gauge where the peak of grip is on the front axle. The self-aligning torque adds a bit of noise to this. We haven't really talked about the difference between self-aligning torque and lateral force and why it matters, but if feel free to go and research that at your leisure. The peak self-aligning torque of a tyre occurs much earlier in terms of slip angle than the maximum of the peak force. And because the drivers are usually driving in torque control, that is feeling the torque through the steering wheel in order to gauge how much front grip they have, that's a big deal. So, we talked a lot. Don't forget the 5 key factors. Those are the most important things you can do for your car. Everything else is second order. We talked about the driver is always limited by grip on a particular axle, or maybe even sometimes on a single wheel, or engine power. And we might be able to increase the car performance envelope by getting some of these aspects right. We've got a few sort of key things that we can play with in order to get the most out of the tyre, deliver the fastest lap time. There's a few here. We talked about weight distribution, mechanical balance, differential, all that side of things. And that's it. Thank you all for your time.